Hi class, today we're beginning with the calculation of an intermediate pH as we continue our acid-base chemistry. So, suppose you are adding aliquots of a 0.1 molar solution of sodium hydroxide to slowly neutralize a 150 milliliters of a buffered solution from example 6. So this is with acetic acid. What is the pH after 20 milliliters of that 1.1 molar solution of sodium hydroxide has been added? Then you get a new total volume of 170 milliliters. So this type of problem is a step towards what we're going to be doing a lot of, which are titration problems. But for now, what we're looking at is a buffered solution of acetic acid and its conjugate base acetate. And we have equilibrium concentrations from the last problem that are 0.25 molar and 0.030 molar. So what we need to figure out is our equilibrium moles, because it is going to be our moles of acid that react with moles of base in a 1-to-1 ratio. So we do that calculation here. Our equilibrium moles are that 0.25 molar moles per liter multiplied by our volume of our solution, which is 150 milliliters. That is our initial solution volume. So 150 milliliters equals 0.15 liters. And we multiply those two values together and we get 3.75 times 10 to the negative second moles of acetic acid. Similarly, we calculate our moles of acetate using the same volume, and we get 4.5 times 10 to the negative third moles of acetate. So a neutralization reaction occurs when you have an acid reacting with a base. So what we need are our new initial moles after the reaction, and that's going to shift and then either give us a situation where we use an ice table or the Henderson-Hasselbalch equation to give us our equilibrium values. So let's see how that happens. First, the neutralization step. That's going to be moles of sodium hydroxide reacting with the acid. So our sodium hydroxide is given at the top. It's 0.10 molar of NaOH. And we have 20 milliliters of that solution being added. So we can take 0.1 moles per liter multiplied by 0.020 moles, and we find out that we have 2.0 times 10 to the negative third moles of sodium hydroxide reacting. The moles of sodium hydroxide that react are equal to the moles of acetic acid that react, and that's because it's a neutralization reaction. So we have acetic acid reacting with hydroxide to form acetate and water. These are all in a 1-to-1-to-1 ratio. So as acetic acid reacts, that amount of moles is going to decrease, while simultaneously increasing our moles of acetate, our conjugate base, and our moles of hydroxide decrease. So we have acetic acid, new initial. That is what we need to calculate before figuring out what kind of shift is going to happen. So we need our new concentration of acetic acid. So we're going to take our 3.75 times 10 to the negative 2 moles of acetic acid, and we're going to subtract 2 times 10 to the negative third moles. That is the number of moles that reacted in a 1-to-1 ratio with our moles of hydroxide. So moles of CH232 that react with the base. So once we subtract those moles, we then need to divide by our volume. Our volume is no longer 150 milliliters, it is now 170 milliliters because we've taken 150, added 20 mils of our sodium hydroxide solution to give us 170 milliliters. So we take our initial moles of acetic acid, subtract the amount that reacts away, and then divide by our new volume, which is larger, gives us a new initial concentration of 0.21 molar for acetic acid. Our new initial acetate concentration, CH3COO-, is going to be that 4.5 times 10 to the negative third that we calculated up here, and we're adding the 2 times 10 to the negative third moles. We're adding because as CH3COOH decreases, the moment we deprotonate that, we by default create more acetate, CH3COO-. So if we take 4.5 times 10 to the negative third moles, add 2 times 10 to the negative third moles, and then divide by 0.17 liters, we get a new initial concentration of 0.038 molar. So what do I mean by new initial? Well, now that the neutralization reaction has occurred, we can now either do a ice table or a Henderson-Hasselbalch equation because we now have new initial values for our HA, our acid, which is 0.21 molar, which we just calculated, and our new initial concentration of acetate, 0.038 molar, which we just calculated. So here what I'm going to do is show this calculation using the Henderson-Hasselbalch equation because that's our new equation. So pH is equal to pKa plus the log of A minus over HA, our conjugate base divided by our acid. Remember, we need to be very sure about how we assign our HAs and A minuses. The Ka for this reaction is given to us. It's 1.8 times 10 to the negative fifth. We can calculate pKa, which is 4.74, by taking the negative log of Ka. Our concentrations of A minus acetate and HA, acetic acid, are now known because we just calculated them. So we can now calculate pH using the Henderson-Hasselbalch equation. So we get 4.74 plus the log of 0.38 molar, or rather 0.038 molar, divided by 0.21 molar, and we get a pH that's equal to 4. And this brings us to acid-base titrations. So in an acid-base titration, we are measuring the pH as we increase the amount of base that's being added. So measured volumes of an acid or base of known concentration are added to a flask that contains a base or an acid, respectively, of an unknown concentration. The concentration of the added solution is known, then the concentration of the unknown can be determined. So here is what a typical titration curve looks like. So this is an acid-base titration, meaning that we are beginning with an acid, and on the x-axis, we are adding base. If it were flipped, it would actually be a base-acid titration. So since we are beginning with an acid, we are starting with our curve down here under acidic pH, where the y-axis is pH. So we have a low value of pH, which is acidic, and as we add base, our pH slowly changes, and then suddenly and abruptly, it flips. We go through a pH of 7, which is neutral, and then we end up with a high pH, which is basic. The point at which it inflects is called the equivalence point. Before the equivalence point, we have an acidic environment, and beyond the equivalence point, we have hydroxide in excess, so this would be basic. So let's look at an example of a titration of a strong acid with a strong base. So here, we are going to calculate the pH of 50 milliliters of 0.10 molar HCl, hydrochloric acid. At this point in the titration, no base has been added yet. So we are right at the beginning of the curve, right down here, and a strong acid with a base titration. So one HCl reacts with H2O, water, to form one equivalent of chloride and one equivalent of hydronium. In this situation, hydrochloric acid and hydronium are in a 1-to-1 ratio, so our hydrochloric acid concentration actually equals our hydronium concentration. So if we're beginning with 0.1 molar of HCl, we know that we have 0.1 molar of hydronium. We take the negative log of that, and we get a pH of 1, and we're done. Now, after 22 milliliters of 0.20 molar sodium hydroxide has been added to the 50 milliliters of 0.1 molar HCl, we need to do a neutralization reaction like in the last example. So in this situation, we have our initial moles of hydrochloric acid. This is going to be really important. So we take our 0.10 moles per liter of HCl, and we multiply it by the volume, 50 milliliters, which is 0.05 liters. And we get 5 times 10 to the negative 3 moles of HCl. This value is going to be the same for all of our calculations. What's going to change is the moles of sodium hydroxide that have been added. At this point, we are at 22 milliliters of 0.20 molar NaOH. So we take 0.20 moles per liter, multiply by 0.022 liters, which gives us 4.4 times 10 to the negative 3 moles of sodium hydroxide that have reacted. Those moles are going to react in a 1-to-1 ratio with HCl. The hydroxide deprotonates 1 proton from HCl, and HCl only has 1 proton. So the remaining moles of HCl can be calculated. They are 5 times 10 to the negative 3 moles, our initial value, subtracting the amount that reacts with base, and we get 6 times 10 to the negative 3rd moles of HCl that remain. We now need our new hydrochloric acid concentration. That's going to be that value of moles, 6 times 10 to the negative 4th, divided by our new total volume, which is 50 milliliters plus 22. And we get that from the problem. That's 50 milliliters plus 22 milliliters. That gives us a new total volume of 72 milliliters, or 0.072 liters. We divide those two values and we discover that our new hydrochloric acid concentration is 8.3 times 10 to the negative third molar. Hydrochloric acid concentration is equal to the hydronium concentration. Again, this is because strong acids react completely. So I didn't draw attention to it last time, but HCl reacts with water, and we have an irreversible arrow here. That is why these are in a 1-to-1 ratio, and that's why we can be confident that whatever the hydrochloric acid concentration is, it's going to be equal to the hydronium concentration. For a weak acid, this is reversible, and there's going to be a Ka associated with it that tells you the relative amount of products to reactants. That is not the case for strong acids. Strong acids dissociate completely. So we have a HCl concentration that's 8.3 times 10 to the negative third molar, which gives us a hydronium concentration of 8.3 times 10 to the negative third molar. We take our negative log of that value, and we get a pH of 2.08. On to our next step, where we have part C. We're going to calculate the pH after 25 milliliters of 0.2 molar NaOH have been added to 50 milliliters of 0.1 molar of HCl. Our initial moles, again, are not going to change. They're 5 times 10 to the negative third moles. So that's why that value is just provided for you from now on. The moles of NaOH that have been added are now different because we have a larger volume. So we have 0.2 moles per liter times 0.025 liters is going to be equal to 5 times 10 to the negative third moles of sodium hydroxide. So in order to figure out what the concentration is of HCl, we need the moles of HCl and the volume. So we take our moles of HCl that we're starting with, 5 times 10 to the negative third, and we subtract the amount of moles that have reacted with sodium hydroxide, which is 5 times 10 to the negative third, which means that 0 moles remain. This is a special situation where you have the moles of acid equal the moles of base. That is the inflection point, which is called the equivalence point. So we are right in the middle of our titration curve. And that is the single point where the moles of acid equal the moles of base. If we flip back briefly to part B, we can see that our moles of acid are greater than our moles of base, so we're still acidic. So for this problem, part B, when we have fewer moles of base than we have moles of acid, we are somewhere before the equivalence point, but we don't really know exactly where. But once we are at a situation where our moles of acid equal our moles of base, we know exactly where we are. So our hydrochloric acid concentration is now 0 because no hydrochloric acid remains. In that situation, and from every situation forward, pH is dependent on the remaining base. So what happens here? Our HCl has completely reacted away with NaOH, so all of this is gone. What we are left with is as follows. So HCl has dissociated, so we have proton and chloride. NaOH has dissociated to form sodium ion and hydroxide ion. That proton and that hydroxide are going to react to form water, and what we're left with is sodium chloride, salt, and water. All strong acid-base neutralizations form a salt and water at the equivalence point. That is true for all strong acids reacting with strong bases. We get a salt and water, and if our byproduct is always water, we are always at a pH of 7. This is always true for strong acid, strong base. Again, this will be different when we are looking at weak acids. Let's move on to part D. So the equivalence point is now behind us. So in part D, we have a calculation for a pH after 35 milliliters of 0.2 molar NaOH has been added to 50 milliliters of 0.1 molar HCl. Our new total volume is 85 milliliters. So our initial moles is 5 times 10 to the negative 3 moles of hydrochloric acid. The moles of sodium hydroxide that have been added can be calculated. That's 0.20 moles per liter times 0.035 liters is 7 times 10 to the negative third moles of sodium hydroxide. The moles of remaining hydrochloric acid are 0, so the pH is now dependent on the remaining base. Again, this is true for every situation that we are beyond the equivalence point, at the equivalence point or beyond. So our sodium hydroxide moles, 7 times 10 to the negative 3, are now greater than our moles of acid. So we are in a situation of the titration curve where we are at the top because we have more base than we have acid. So the pH is dependent on that remaining base, and we can solve that in a couple of ways. So excess moles of sodium hydroxide, that's what we need. So we have 7 times 10 to the negative third. We subtract 5 times 10 to the negative third. That's the amount that reacted with hydrochloric acid. And what we're left with is 2 times 10 to the negative third moles of sodium hydroxide. We can take 2 times 10 to the negative third moles of sodium hydroxide and divide by our new total volume of 0.085 liters, and that gives us our hydroxide concentration, which is 2.4 times 10 to the negative third molar. We can then get to pH two different ways. We can get to pOH by taking the negative log, and then we can get to pH by subtracting from 14. And those values come from the autoionization of water. We could also directly convert from hydroxide concentration to hydronium concentration using the autoionization of water, and then we can convert from hydronium to pH, which also gives us a pH of 12.4, which is a high pH and is basic.